Now we turn to searching. Let's quickly recap the two ways to find a value in an array and see why sorting makes the fast one possible. Linear search is the search that always works. It does not care if the array is sorted or not. This array is unsorted and we look for the value 23. A marker walks the cells one by one, starting at index 0. Our checked count is 0. We check index 0. The value is 7. 7 is not 23, so no match. Checked count is now 1. Step right. We check index 1. The value is 2, not 23. Checked count is 2. Index 0 is dim now, ruled out for good. We check index 2. The value is 8, still no match. Checked count is 3. Keep walking right. We check index 3. The value is 5, not 23. Checked count is 4. 3 cells are dim behind us. We check index 4. The value is 23. That is a match, shown in green. Checked count is 5 and we return index 4. 5 checks to find it. Binary search would have dropped half the cells each step, but binary search needs a sorted array. Linear search checks every cell instead. Here is linear search in C. It takes the array, its size, and the key you want, and it returns an index. The loop scans every slot, from 0 up to n-1. At each slot it compares against the key. On a match it returns the index straight away, so it stops early. And if the loop falls off the end, the key is absent, so it returns -1. There is no pseudocode for this one, deliberately. Textbook pseudocode would be a near verbatim copy of this loop. The cost is big O of 1 in the best case, if the key is first, and big O of n on average and in the worst case. The one thing worth noticing, it needs no ordering at all. Now binary search. This array is sorted and we look for the value 38. We keep a window, the part still in play. At the start the window is the whole array. The low marker is at index 0 and the high marker is at index 10. Probe 1. We look at the middle of the window, index 5, which holds 23. 23 is less than 38, so our value must be to the right. We drop the whole left half. The left half is now dim, ruled out. Probe 2 looks at the new middle, index 8, which holds 72. 72 is greater than 38, so we drop the right half too. Probe 3 looks at index 6, which holds 38. That is a match, shown in green. We found it in 3 probes, not 11. Each probe cuts the window in half, so the cost grows like log base 2 of n. This only works because the array is sorted. When the data is sorted, you can do something much better. Binary search throws away half of the remaining values on every single comparison. Let's read the pseudocode. We set low to 0 and high to n-1. Those two bounds mark the interval we are still searching. The loop runs while low is less than or equal to high. We compute mid, the middle index. If a at index mid is equal to the key, we found it, so we return mid. If a at index mid is less than the key, the answer must be to the right, so we move low to mid +1. Otherwise it is to the left, so we move high to mid -1. If the interval empties out, we return nil, meaning absent. And here is binary search in C, matching that pseudocode. Low starts at 0, high at n-1. Those two together are the interval we are still searching. The loop runs while low is less than or equal to high, that is, while the interval is not empty. We compute the middle as low plus, high minus low over 2. Written this way it cannot overflow, even on very large indices. If a of mid equals the key, we found it. If A at mid is less than the key must be to the right, so low moves to mid plus 1. Otherwise it is to the left, so high moves to mid minus 1. Either way, half the interval is gone. And when the interval empties, we return minus 1. Note the comment. Minus 1 is an index sentinel, not null. Binary search costs big O of log n, but read the condition attached to it. It requires a sorted array. And that requirement is exactly what the rest of this chapter builds toward. One note on sentinels from chapter 2. An index search returns minus 1, not null. Null is reserved for the operations that return a pointer.